All right, y'all, welcome to part 3 and my final part of energy. This is the law of conservation of energy. Basically, conservation means we don't lose anything. So this basically states that the energy in a system remains the same. Little asterisk is it's neither created or destroyed. It only changes form. So energy can change from one kind to another, but there is no way it can ever be created or destroyed. This is the law. You cannot break it without breaking the universe in some fundamental way. Now, we can express this with an idea. The total energy is equal to all the kinetic energy plus all the potential energy plus any light energy. But we're not really going to be talking about this much, so I'm just ignoring it for now. So yeah, we don't really have to worry about this one, at least in this video. Maybe we'll do it something later. But for now, total energy of a system is the kinetic energy plus the potential energy. And there's no real good way to do this other than to just start doing some examples. So in this example, I take a baseball that weighs, let's say it weighs 1 kilogram for the sake of this argument, and it is a whole 5 meters off the ground. So this baseball is a whole 5 meters off the ground, and I should say example 1. And we will drop this from rest. Now, I just said rest as a kind of scientific way of saying from no movement. Basically, it means you just hold something and then you drop it. Rest means it's not moving. There's no initial velocity. So no movement, in other words, V initial is equal to 0. So the question is, as this baseball travels down, right before it hits the ground, what is the velocity final? How fast is this baseball traveling before it hits the ground? How fast is the ball traveling before it hits the ground? So what we want to do is kind of break this into two ideas. We want to look at the total energy initial, and we want to look at the total energy final. We want to look at the start and at the end of our example because total energy is going to be the kinetic energy initial plus the potential energy initial. And whatever energy we start with must be equal to the energy we end with because of the law of conservation of energy. Therefore, that's going to be equal to our kinetic energy final plus potential energy final. And these will be equal because it's the law, specifically this law right here. Conservation of energy says the energy at the beginning must be equal to the energy at the end. We can change it. In fact, we absolutely will change it. but these energies must be the same. So let's go ahead and look at our equation. Total energy initial must be equal to total energy final. And we're going to go ahead and break this up even further. I'm going to actually take this and move it down here. I'll keep this equal right in the middle. So our total energy initial is going to be kinetic energy, and I'm going to start using I for initial, plus potential energy initial. Our total energy final is going to be kinetic energy, F, again, F for final, plus potential energy final. Now, initially, we have V equals 0, which is going to be really important, but let's go ahead and solve anyways. Kinetic energy is 1/2 mv initial squared. You'll notice that mass is not initial because mass is going to stay constant. The mass in the beginning and the mass at the end will always be 1 kilogram. So we don't actually change mass. Plus potential energy. Now potential energy is going to be mass again, plus gravity, and gravity also doesn't have an initial because gravity is always the same throughout, but our height is going to change. So we're going to have a height initial. All right, just like we expanded the left side, we're going to expand the right. So 1/2 m, now it's V2 squared plus mgh final. Oh, and sorry, my bad. I said V2, but again, we're talking about initial and final. So I'll throw a little F there. So what we're going to do is plug in some values, but right before we plug in some values, a little bit more housekeeping. What I can do is divide each of these by mass. And I'm dividing the left side and the right side by mass. And basically that allows me to just cancel it out. And that way there's one less thing to deal with, one less variable. All right, so let's go ahead and start filling these in. 1/2, our initial velocity, we know from right here, it's gonna be 0. So it's 1/2 times 0 squared plus our gravitational constant, 9.8, times our height, initial, and we're initially starting out at 5 meters. That right there is going to be our H initial. So we can just go ahead and multiply this by 5. Now on the right side, we have 1/2 again, but we don't have a V final. This is what we're looking for. So I'm just going to go ahead and leave this variable as V final squared. Then I'm going to go ahead and add in our gravitational constant, 9.8, times our height final. Now, right before something hits the ground, we are looking at it at the moment it hits the ground. If something is hitting the ground, it is actually at a 0 height. Now, these zeros, both on the left side and right side, are really convenient because it means all of that is just going to be 0 because it's going to equal to 0. And all of that's going to equal to 0. And we know that just because anything times 0 is, well, 0. So our final equation comes out to be 9.8, and we'll use our full units, meters per second squared times 5 meters, remember that's height and gravity, is equal to 1/2 V final squared. Now I want to get rid of that 1/2, so I'm going to go ahead and multiply both sides by 2. And when I multiply both sides by 2, I get rid of the 1/2, and I get a total of 2 times 5, which is 10, times 9.8 becomes 98. And then m times m is meter squared over second squared is equal to V final squared. The last thing I have to do here is just go ahead and take a square root of this function. So I'm going to go ahead and square root both sides, and I get V final, sorry, I like my V's on the left side, it's just who I am, is equal to about 9.9 meters per second. You'll notice the units also get squared. Now, this is how we use conservation of energy to solve a problem. It takes quite a bit of work, but once you get good at recognizing where you can cancel out certain terms, you get much faster at it. So let's go ahead and do one more example. Now, this one's going to be quite a bit harder. So for this next example, oh gosh, I just had it up. We are going to, instead of starting from rest, we're actually going to start with some kinetic energy. In fact, we're going to have kinetic and potential energy on both sides. So that can definitely make things more difficult, but I think we are ready to try one if you are. So what we're going to do is we're going to take a ball and we're going to throw it up at an initial velocity, but I'm not going to tell us what that initial velocity is. Instead, we're just throwing it up. Furthermore, we're going to do this from 12 meters off the ground. So we're starting with a ball already being 12 meters off the ground, therefore we're going to have potential energy. And because we're throwing it up, we have initial kinetic energy as well. So before we solve this, I want to just add one more additional detail. We're actually going to give this an initial velocity as well as 10 meters per second, but this time upwards. What I want to find, once again, is when the ball is just about to hit the ground, when height final equals 0, what is the final velocity? Now, we can solve this in very much the same way as before. If we look at our total energy in the beginning, initial, that's going to be equal to our kinetic energy, initial, which we now have, plus potential energy, initial. However, our total energy final, because now we have a height of 0 at the end, is only going to be kinetic energy final. And we can just take out the idea of potential energy anyways, because we know it's not going to exist there. So we're going to set these two equal to each other and just start plugging and chugging the variables. KE initial is going to be 1/2 mass times our velocity, 10 squared, plus potential energy, which again is mass times 9.8 times 12, which is going to equal to our final kinetic energy, which is 1/2 mass again, V final squared. Now, once more, we don't even have to worry about mass because it appears everywhere. We can just cancel it all out. And then all we have to do is just solve this problem. 10 squared is going to be 100. So 1/2 times 100 plus 98 times 12, which 9.8 times 12 will come out to 117.6. And that's going to be equal to 1/2 times V final squared. So if we add everything up on the left side, it's 50 plus 117.6, which is going to be 167.6, which we will then multiply out this 2. And that's just going to go ahead and give us 335.2 is equal to V final squared. That was a little bit of confusing math, but once again, all I did is I multiplied this to get 50. 50 plus 117 gets 167. I multiplied out the 2, giving us 335.2. And then all we have to do is do a square root. And we get our V final is going to be 18.3 meters per second. And that's about as hard as it gets. Just a little couple trick things that we ask usually is if you throw a ball up, when a ball is at the peak of its upwards movement, the velocity is going to actually be equal to 0. Because right at that peak where it's between up and down, it's going to be 0. So something to watch out for is what is the kinetic energy at the peak of an arc, which is going to be 0 because velocity is 0, or what is the potential energy because it will all be potential. With that said, have a great night, and I hope these videos help.